Okay, let me do a roller coaster problem. I'll ask you a couple questions about it. Let's take a real roller coaster, the Intimidator at King's Dominion, and let's just say that and look up. You can look up the stats, and the stats say that it's got the first hill height is 305 feet. I'm assuming that's 305 feet above the lowest point that the roller coaster car reaches, not above the ground, which is different. And the top speed of 90 miles an hour. So basically, you've got a roller coaster goes up a big hill, and then it comes down and then does something else, right? So we're basically saying that this big hill is 305 feet above the ground, and that at this point the roller coaster car has a speed of 90 miles per hour. 90 miles per hour, right? That's miles per hour. Okay. So we ask about this. First of all, you got to recognize that roller coasters are powered by the first hill, right? How does a roller coaster work? You put it on a chain lift and you lift it up to the top of the first hill, and then you let it go from rest, right? V initial equals 0. And the whole rest of the way is powered by gravity. Most roller coasters, not all roller coasters, but most roller coasters, powered by gravity. So the first question is what is the largest hill that the roller coaster could then go over after that? In other words, let's make it go back up a hill. What is the largest hill? We call that H1. How big can H1 be? I think the answer is obvious, but in case it isn't, let me just say, let's just ask that question. We're going to start by assuming that the frictional force is 0. Assume there's no frictional force, which is not a reasonable thing on a roller coaster. Otherwise, roller coasters would not work because we can't get rid of friction. If we assume there's no friction, we wouldn't build them right. But let's assume there's no friction and do a work equals change in kinetic energy problem. Saying we know what H is, the first hill height. We know what V is at the bottom. Let me call that VBOT, V bottom. And we want to know, if it goes back up the hill, how high can it get, H1? So, actually, I said one thing which probably is not. The fact that it's 305 feet tall and the highest speed is 90 miles per hour, that does assume friction. That assumes friction. That's because that's real. That's a real roller coaster. But let me just say, let's ignore the fact. So if we're assuming there is no friction, then the V at the bottom is actually going to be larger than 90. V at the bottom is going to be bigger than 90 miles per hour because of friction. So let's just say we don't know what it is. We'll just use V at the bottom. Okay. But we actually don't even need to do that, because what we can do is, and I'll explain what I mean in a second. If I take, let's go ahead and take the roller coaster starting at the top and starting at the bottom, and let's do work total equals change in kinetic energy between the top and the bottom, ignoring friction. So therefore, the work done. So we can draw a free body diagram of the roller coaster car at any arbitrary point on the track. And if we draw it at some arbitrary point on the track, there's going to be a normal force in that direction, gravitational force in that direction, and that's it. So the total work done, while it equals change in kinetic energy by the work energy theorem, by the definition of work, is going to be the work done by gravity plus the work done by the normal force. We've already argued that the work done by the normal force is 0 because it is always perpendicular to the displacement, even if the track is wonky. And the work done by gravity is always mgh, where h is the downward displacement, or negative mgh if h is the upward displacement. So that's easy. So we can therefore say mgh is equal to 1/2 mv final squared minus 1/2 mv initial squared for a roller coaster without friction. So all we care about is if it goes through a height h, we know what the change in velocity is going to be. Yeah, so maybe we should first ask the question. Let me ask the question. Let's make this part B, apologies, and part A, what is the ideal speed at the bottom? What is speed? Whoops. We've actually answered this question numerous times in other problems, but we can go ahead and solve V final from this equation, and what you'll find is that V final is equal to the square root of 2gh, and so the ideal speed, if there was no friction, would be the square root of 2 times 9.8 meters per second squared times h in meters. We got to do a conversion. Doing the conversion with 3.28 feet in 1 meter. What we get is, oops, look at my calculator. Darn it, calculator. 93.0 meters. 93.0 meters to 3 significant digits. Gives me 42.7 meters per second. You say, ooh, that's a lot less than 90, but you say, no. So 90 is not a lie. Those are different units. We got to convert it to miles per hour. Done the conversion there in case you want to do it yourself, but 95.5 miles per hour. Okay, so friction doesn't seem to, if they're probably exaggerating this a little bit, but friction doesn't play a huge part. We only lose 5 miles an hour because of friction. I'm sure they're rounding anyway. Let's go ahead and just use that to determine how high it will go over the next hill. Again, I hope that B is going to be obvious, but maybe it's not, so we should do it. B, how high can the next hill be? So we can say we're going at some, we'll just call it VF, and we know what VF is. And then when we get up to the top of the next hill, and we want to know how high can the next hill be? So how do we really answer that question, how high the next hill can be? Well, we can do a work total equals change in kinetic energy again. And as you go from here to here, right, there are, again, two forces on you, the normal force and the gravitational force, mg, Fn, and the work total is the work done by gravity plus the work done by the normal force equals 1/2 m v final squared minus 1/2 m v. Oops, now I got to be careful here. This, I called this v bottom, not v final. That v bottom, because now this work total could change. This is the initial and this is the final, right? Final is at the top now, so we should call these top and bottom. So therefore, the work done by gravity plus the work done by the normal force is equal to 1/2 m v top squared minus 1/2 m v bottom squared. If we're going from here, the bottom, to here, the top. But what is v top? If we want the biggest hill possible, then that just means v top equals 0. It just has to have a slightly higher than 0 velocity, right? Slightly higher than 0 to get over that hill. If it's 0 exactly, it's going to stop right at the top. It's just a bit higher. It's going to be greater than that. It's going to go over. So we can just set v top equals 0 as our limit. And remember, work done by gravity, mgh, work done by normal force, 0. But we're going up. Right, we're going up a height h1. So this is going to be, because we're going up a height h1, is going to be minus mgh1. Right? Work done by gravity is always mgh, where h is the vertical displacement. It's negative if you're going up, and it's positive if you're going down. Hence, I'm just writing the negative sign out front here, putting absolute values to make sure we know that that's a negative value. Minus mgh equals 1/2 mv top squared, 0, minus 1/2 mv bottom squared. But v bottom is 95.5 miles per hour. Actually, v bottom is square root of 2gh, the original height of the hill, right? So 1/2, and we can go ahead and plug in v bottom was square root 2g original height squared. And we can solve this, and we get minus mgh1 equals minus 1/2 m 2gh. The 2's cancel, and we get, oh, lo and behold, we get minus mgh1 equals mgh. So therefore, h1 had better equal h, right? Hopefully that was obvious, that if we start at the top of a hill h, the roller coaster can never go higher than that. That's energy conservation. That is a statement of energy conservation. If we're starting from a speed of 0 at the top of the first hill, the roller coaster can never go higher than that. Unless we add energy to the system. If it's only under the influence of gravity, if it's only under the influence of conservative forces, it can never go higher than that. That hopefully is obvious. And actually, because of friction, it can't go that high. So because of friction, because this speed is actually a little lower than the ideal speed, it can't go as high. So a roller coaster is always that, right? The first hill is the highest, the second hill is the next highest, the third hill is the next highest, because we're always losing energy because of friction. Friction is always taking away energy, so we can never get over a hill quite as high as the last one. And then loops are a whole different thing. Loops are a whole different thing, which we'll talk about another time. Well, you certainly couldn't go around that loop because that loop is higher than that hill. But that's a whole nother thing. It's not as obvious. Ask part C. Part C is going to be, what is the frictional force? So what is the average frictional force? Let me start with, what is the work done by friction as the roller coaster goes from the top of the first hill to the bottom of the first hill? And then we'll talk about what we need to know in order to ask what's the average frictional force. What is the work done by friction going from there to there? Well, we can do work total equals change in kinetic energy, and the forces at any one time are a normal force, a frictional force. We now have to add the frictional force in, and the gravitational force. So that is a free body well, it's not a free body because I didn't take it off the track, but that is a force diagram of the roller coaster car at any instant. So we've got the work done by the frictional force plus the work done by the normal force plus the work done by the gravitational force is equal to 1/2 mv final squared. V initial is 0, v0 equals 0. So we could put in that 1 minus 1/2 mv initial squared, but recognizing right away that's 0. Okay, so we can go ahead and say, well, we know that that one's 0, and we know that that one is mgh, right? Every time. So the work done by the frictional force plus mgh equals 1/2 mv final squared. And so therefore, the frictional force is 1/2 mv squared minus mgh, and it's a plug-in. Except for the fact that what do we need to know that I didn't give you? And that's the mass of the roller coaster car. I looked up the mass of the roller coaster car. Sorry I didn't give it before, but the mass of the roller coaster car is something else we need to know to answer this question. And it's a somewhere around, they're not too light. It's like a car, 4,500 kilograms. That's pretty darn heavy. I mean, there's a bunch of cars together and people in it, right? But anyway, that's what we get, and we can go ahead and plug in our numbers. 1/2 4,500 kilograms times V final. Now careful, units, 90 miles per hour, 305 feet, kilograms, and G is 9.8 meters per second squared. We got to put everything in the same units, so I'm going to go ahead and convert this, the height. So convert the miles per hour, convert the height, 3.28 feet, and plug those numbers in, and you get... So the work done by friction is minus 465,210 joules. Oh my gosh, does that make any sense? Well, first of all, does the minus sign make sense? Does the minus sign make sense? Yes, it does, because the work done by friction is trying to slow down the car, so it should be negative work. Does the number make sense? Well, it's a very heavy car. Think about what the work done by gravity is. The work done by gravity is 4,500 kilograms times 9.8. Well, right here, sorry. Well, that's the work done by gravity. I mean, that's a large number. That's actually 4,500, 45,000 times 100. That's 10 times this number, right? That's 10 times this number. So this is only a tenth of the energy, which makes sense. The work done by friction should be small compared to the work done by gravity. Otherwise, the roller coaster would be no fun. Do you get that? Right. So this factor here is about 10 times as much as this. And that makes sense because gravity is what's doing the work that makes the roller coaster fun. It's what speeds up the car. If the friction is going to be slowing down the car significantly, that's no fun. You want to make the friction a lot smaller than the gravitation, or the work done by friction a lot smaller than work done by gravity, so you can get that speed. And that makes sense because we already showed that there isn't a whole lot of speed difference, right? It's only a 5-mile-an-hour speed difference. So the work done by friction shouldn't, look, and that's about 5%. And it's about 10%, so that's not so bad. Okay, so there you go. That's the work done by friction. So the last question I want to ask is, if I know that the work done by friction now is this, how could I use that to figure out the frictional force? How can I use that to figure out the frictional force? In order to figure out the frictional force, I would have to use the definition of friction. Definition of friction is the magnitude of the frictional force times the displacement times the cosine of the angle between them. But now what displacement is this? Well, let's look at the roller coaster car at some arbitrary place on that track. And let's say, oh, look, the frictional force is always pointing backwards and the displacement is always pointing forwards. No matter where you are, the frictional force is always pointing backwards, and the displacement is always pointing forwards. So the first thing to recognize is that this theta is 180 degrees, and that's what gives us our minus sign. And cosine of 180 is minus 1. D is the length of the track, right? Because D always points forwards. It's really just at any point, it's how far I've gone along the track. It's how far I've gone along the track. So at any point, even though the angle of F and D changes as we go down the track, the angle between them doesn't. The displacement is always in the forward direction. So D in this case is the length of the track. The D is, so what we're really doing is we're adding them up. We're saying, okay, let's assume it's about that it's not changing between here and here, and so it's that little bit of D. And then assuming it's not changing between here and here, it's that little bit of D. Assuming it's not changing between here and here, it's not changing angle. That's what I'm saying, not changing angle. And so that little bit of D, and then we're just going to add up the work of all of those as we go along, and that's just the total length of the track. D is the total length of the track. D is total length of track. And so we would have to know the total length of the track in order to find, from our starting position, initial, to our finishing position, final, to find our force of friction. We need to know D. We have to know D in order to know FF. And D in this case is actually, in this case, it's not H, it's the length of the track for the frictional force. And so you can actually figure this out. Essentially, you can look at the Intimidator, because remember, we're talking about a real roller coaster, and you can actually figure out by looking at the geometry that length of track is about 320 meters. It's a pretty steep hill. Remember, the height of the hill was 305 meters. So D is approximately 320 meters, and we can go ahead and plug that in. And plug that into work minus 465,000 FF D cosine theta. And solve for FF, therefore FF is equal to, remember, FF is a magnitude because this is a magnitude and this is a magnitude, and it's 1,454 newtons. Again, is that a lot? Well, remember that the weight, mg, is about 45,000 newtons. So it is, doesn't seem like a huge number compared to the weight. It doesn't play a huge part. It does slow it down a little. It doesn't slow it down a lot.